The lecture on the nomenclature of organic compounds. There are a certain set of rules that you need to follow to write a name of an organic compound from a given structure and vice versa. By the end of this lecture, you will be prepared to solve any problem regarding nomenclature given in your tests. So let's begin. You have a structure given. The first thing you need to decide on is finding the suffix of the name. Now the suffix of the name depends on the longest chain of the compound that is possible. It also depends on the functional group of the compound or the principal functional group of the compound, which I will be dealing with later. Now I will be sticking with simple hydrocarbons, that is alkanes, the compounds which do not have any functional group. Now in this given structure, if you want to decide on the longest chain in the structure, you have to find the chain that has highest number of carbons. Now in this case, that would be this black chain because it has 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. Or alternatively, you can also choose this as your longest chain because it too has 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. But either way, you will end up with the same name because both the paths are identical. There is no difference in both the paths. This is the chain length rule, and the chain length rule decides what the suffix of the name of the compound is, or what the parent chain or the main chain is. And we have to choose the chain with the largest number of carbons or the longest chain possible. In the case of a molecule where you have two dissimilar paths giving you the longest chain, you have to decide using a tiebreaker. Here the paths of the two longest chains was same, this chain and this chain. But what if both the paths are different? If you look at this compound, there is more than one path that can give you the longest chain. Precisely speaking, there are 3 unique paths here. Let me explain. Here, if you choose this path, it has 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. Or you can choose this path, which also has 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. And there is a third possibility here, which too gives you 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. There are actually 4 paths. This path, this path, this path, and this path. But these 2 paths are identical. So there are 3 unique paths. Now, in case of this tie, we use tiebreaker here. If more than one path leads to the longest chain, choose the one which has the most substituents. Let me explain. If I choose this chain as my longest chain, it has only 1, 2, 3 substituents. And if I choose this chain or this path as the longest chain, it has 1 and 2 substituents only. But if I choose this black path, then it has 1, 2, 3, and 4 substituents. So I have to choose the black path, or I can choose this path also, which is identical anyway. And based on that, you will have the name of the compound, details of which I will be dealing with later. Now, after choosing the longest chain, the next thing is to identify the substituents. Now, generally, the substituents end with suffix "-il". Here, this is the suffix of the name of the compound, and here you have the substituents. You see all the substituents end with "-il" because generally they are all alkyl groups. Next, after identifying the main chain, which gives you the suffix and identifying the substituents, you need to arrange all of them together. After identifying the substituents, we need to give the substituents their locants. Locants are the numbers of the carbons on the parent chain on which the substituents are attached. In other words, they give you the address on the parent chain where the substituent is attached. For that, we have to give numbering to each carbon on the parent chain. For example, in the first compound, if I number the longest chain, I can either number from here. If I number from here, what do you have? You have substituent on carbon number 5, 2 substituents on carbon number 6, and 1 substituent on carbon number 7. Now if I add all the locants, which are the numbers on which substituents are attached, it's 5 on which one group is attached, on 6 2 groups are attached, and on 7 there is one more group attached. If I add 5 plus 6 plus 6 plus 7, what do I get? 5 plus 6 plus 6, because there are 2 substituents attached there, plus 7. What do I get? I get a number that is equal to 12 plus 12, 24. But if I number from here, I see the locants and add all the locants. It's 3 plus 4 plus 4, because 2 substituents are attached on 4th carbon, plus 5. What do I get here? I get 8 plus 8, 16. So the numbering which gives you the lowest sum is the correct numbering, or the correct way of addressing the locants. Let me explain here. That's why the name that is given here is according to the numbering from the right and not from the left. This is called the lowest sum rule. Here you have your lowest sum rule. It says number your chain from one of the ends on the longest chain, or the backbone or the main chain, such that the sum of all the locants is lowest. It is called lowest sum rule. Fine. What if you have a tie in the lowest sum rule? For example, in this structure, if I number from left, the sum of the locants is 3 plus 7 equals to 10. But if I number from right, the sum of locants is 3 plus 7 equals to 10. Now how to choose between the first way of numbering and the second way of numbering? Here we have a tie. In case of tie, you have to choose in such a way that the lower number comes to the substituent which comes alphabetically first. Here it is an ethyl group, and here you have a methyl group. Now if I number from left, ethyl group gets 3 and methyl gets 7, which is wrong, because ethyl comes before methyl alphabetically, so it must get 3 and methyl should get 7. So this is the correct way of numbering, because 3 is ethyl and on 7 is methyl, and not the vice versa, which is alphabetically incorrect way of numbering. Okay, that's the tiebreaker for numbering. Let's go for the next slide. Now if you have more than one substituent at a single carbon, you need to write the locant twice. Here, what is the correct way of numbering? Is it from the left or is it from the right? It's quite simple to see here, because there are only 2 and that are closer from the right end rather than the left end, so we need to number it from here. So it's 10 carbons, that's why it's decane, and there are 2 methyl groups, that's why I write dimethyl, and I need to mention the locant twice. If there are 2 substituents, I need to mention the locant twice. That means, for example, if you have a methyl group attached on second carbon twice, the correct way of naming is 2,2-dimethyl, not 2-dimethyl. That's one thing that you need to keep in mind. And then the final assembly. After you have decided on the main chain or the suffix of the compound, and then you have identified all the substituents, you have numbered it correctly according to lowest sum rule, and in case of a tiebreaker, going with the numbering which gives you the lower number for a substituent that comes alphabetically first. The next thing is final assembly. How to assemble the name. When you are assembling the name, for example, in this compound, if you see, you have written the suffix because it has 10 carbons. Let me write down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, what is the correct way of numbering? Should I number from left or should I number from right? If I number from left, methyl gets 4 and isopropyl gets 7. But if I number from here, I get 4 for isopropyl and 7 for methyl. Now, according to the lowest sum rule, there is a tie here. 4 plus 7 is 11. And 7 plus 4 is also 11. Which will I choose here? I'll go through alphabetical order. Now, the lower number should be given to the group that comes alphabetically first. Here, it's I before M because I comes before M, and isopropyl starts with I and methyl starts with M. So it's correct to give 4 to isopropyl and 7 to methyl rather than giving 4 to methyl and 7 to isopropyl. Now we need to keep certain things in check or in memory while deciding on the alphabetical order of the substituents. Let me tell you what. If you have things like dimethyl here, trimethyl, tetramethyl, etc., you do not consider D, T, or T to decide on the alphabetical order. You have to ignore di, tri, and tetra. That means you have to not consider di, D for di, T for tri, and T for tetra in giving alphabetical order. For example, if you have dimethyl, trimethyl, and tetramethyl, in all cases you consider M for alphabetical order and not D, T, or T. And in case of substituents like N-propyl, which is a straight propyl, you do not consider N. The only exception is iso. If you have isopropyl, in that case you do not consider P for alphabetical order, you consider I. And if you have isobutyl, you do not consider B, but you consider I. So in all the substituents, all the different names you have, you do not consider alphabetical order for prefixes like di, tri, tetra, or N. But when you have iso, you consider I for the alphabetical order. Here again, you have two substituents. One is isopropyl, this is isopropyl, and you have methyl here. Now what do you consider for alphabetical, for deciding on alphabetical order? In the case of isopropyl, you take I, and in case of methyl, you take M. Next, in this compound, you have two groups again. If I number, this is the longest chain with 10 carbons. We have two substituents at carbon 4 and one substituent at carbon 7. Two methyl groups on carbon 4 and one ethyl group on carbon 7. Now if I apply the lowest sum rule, what do I get? You get 4 plus 4 because methyl is attached twice there, plus 7. So it's 7 plus 4 plus 4, which is 7 plus 8, and 7 plus 8 is 15. But if I number it from here, if you add all the locants, you have 4 plus 7 plus 7 because there are 2 methyl groups there. So here you have 7 plus 7 is 14, 14 plus 4 is 18. So here the lowest sum rule decides from which side you need to number. You need to number it from left and not right, because 7 plus 7 plus 4 is how much? It's 18, whereas if you number from right, it's 7 plus 4 plus 4, which is 15. So 15 is less than 18, so the correct numbering is from this side, not this side. Fine. After numbering, which comes first here? Here, 4-isopropyl came first. You know why? Because I comes before M. But here, 7-ethyl comes before 4,4 dimethyl, because E comes before M, and I'm not considering D for alphabetical order. If I consider D, then 4-dimethyl should have been here and 7-ethyl should have been here. I hope you keep all these intricacies in mind while naming a carbon chain or a compound given to you. So let's go to the next topic. Let me go to the next slide. Now here there are certain bunch of compounds given whose names you need to write. Let me see. If you try to find what the longest chain is, it's obvious that it's this black line. You try finding any other path and it will have less number of carbons than this path. So let me see, how many carbons do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. That's dodecane. Now, should I number it from the left or should I number it from the right? Now, if you look at the structure, you can guess that most of the substituents are towards right and not towards left. Let me take a pen and do it for you. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is a color, a blue. Let me number the other way using some other color, say green. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Now if I consider the blue numbering, what is the sum of the locants? It's 3 plus 6 plus 7, which is 3 plus 6 is 9, 9 plus 7 is 16. So if I go according to the blue numbering, the sum is 16. Now if I consider the green numbering, it's 6 plus 7 plus 10, which is, I think, 17 plus 6 is 23. So according to the lowest sum rule, which is the correct way of numbering, this is the correct way. So what group is attached at 3? At 3 you have a methyl group, so I have written 3-methyl here. And what group is attached at 6? This is 1, 2, 3, 4, 5 carbons. And if you see this carbon which is attached to the main chain, it's a tertiary carbon. That's why it's called terpentyl. And here if you see, you have 1, 2, 3, 4 carbons, so that's a butyl group. And the carbon that is attached to the parent chain is a tertiary carbon. That's why the substituent is called tert-butyl, and it is attached at carbon 7 according to the blue numbering. So the name is dodecane because it has 12 carbons, and there are 3 substituents. Now I need to decide which substituent comes first, which comes second, and which comes third. Now whenever you have tert-butyl, you need to consider B for alphabetical order, and for methyl M, and for terpentyl I need to consider P. And we know that B comes before M and M comes before P. That's why this is the order in which you place your substituents. And these numbers are called the locants. So the locants are the numbers which give you the address on the parent chain where the substituents are attached. In other words, the locants tell you on which carbon is the substituent attached to on the parent chain. In the next structure, if you see, the longest chain is this black chain again, because obviously you cannot see any chain that is longer than this. So if I number this 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it has 12 carbons, that's why it's dodecane. And is this number incorrect? This purple number incorrect? Or should I number from the other side? Let's check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Now let us check the lowest sum rule. Here you have one substituent, so let me write 10. Here I have another plus 7, and here I have another, so let's write 6. So what is 10 plus 6 plus 7? I think it's 16 plus 7 equals 23. Now according to the numbering which is given in blue, if I add all the locants, it's 3 plus 6 plus 7. So it's 3 plus 7 equals to 10 plus 6 is 16. So according to the lowest sum rule, the blue numbering is correct. So the name is what? On carbon number 3 we have methyl, so I write 3-methyl. And on carbon number 6, what do we have? 1, 2, 3, 4. There are 4 carbons, so it must be butyl, right? And the carbon on the substituent that is attached to the parent chain is a secondary carbon. That's why it's secondary butyl. So this is secondary butyl. And here you have an isobutyl. When is a substituent or a compound called an iso? Whenever you have this V shape at the end, or a shape like the sides of isosceles triangle, 2 methyl groups attached to 1 carbon, it's an iso. It has 1, 2, 3, 4 carbons, that's why it's butyl, and it has V at the end, that's why it's iso. That group is isobutyl group. Now how to arrange these substituents along with their locants in front of the suffix? So for that, what do I need? I need to look at the alphabetical order. Now in secondary butyl, I look at B, I don't look at S. And in isobutyl, I look at I because that's an exception. And methyl, I look at M. Now tell me which comes first. B comes before I and I comes before M. That's why this substituent is written first, and then isobutyl, and then methyl. The order of arranging your substituents is not dependent on the locants. It's dependent on the alphabetical order. So that's how the things are done. So let me clean this up. Now let's go to the next structure. In the next structure again, the longest chain is represented in black color. Now I have given black color to all the longest chains, but in your exam or the test or any question, there is no color coding for the longest chain, and you have to identify the longest chain. Now you can do it either through your intuition by just looking at the structure and guessing what the longest chain is, or if there looks 2 potential candidates as longest chains, then check them individually, one by one. Whichever gets the higher number of carbons should be chosen as the longest chain or the parent chain. Sometimes identifying the longest chain is straightforward. You can just look at the structure and decide. Sometimes when the chain is complicated, you use trial and error and check. Now here, I can see that this black chain is the longest chain, and I'll try to number. So if I number it from the left, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's why it's dodecane. Now is this purple numbering correct? Or if I number from right side, say in blue color, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. will I get the correct nomenclature or the correct name? Let me use the lowest sum rule and check. According to the purple numbering, you have a substituent at place 6, and I have another substituent at place 7, and we have one more at carbon number 10. So what do I get here? So it's 7 plus 6 is 13, 13 plus 10 is 23. Now according to blue numbering, if I count 3 plus 6 plus 7, so it's 3 plus 6 plus 7. So 3 plus 7 is 10, 10 plus 6 is 16, so this is correct. So purple is wrong and blue is correct. So the correct numbering is numbering from the right end rather than from the left end. Now let me look at the substituents. At carbon 3, what do I have? At carbon 3 I have a methyl group, that's why I write 3-methyl. And at carbon 6 I have 1, 2, 3, 4 carbons, so it's a butyl group, and we get V at the end, so that makes it isobutyl. And there is another isobutyl here. So isobutyl is present at both carbon 6 and carbon 7. That's why I write it as 6, 7, because it is appearing twice. I write diisobutyl. So the name is 6, 7 diisobutyl 3-methyl dodecane. Next thing was the decision to arrange the order in which the substituents are placed in front of the suffix. For that, you check alphabetically. In methyl, I consider M. In diisobutyl, I don't consider D, but I consider I, because di, tri, tetra, N, all these things are to be ignored, but iso is not. So I comes before M, so this substituent is written before this substituent. That's why the name is written as given. Fine. Let me go to the next slide. So in the next slide, there are more structures given. One thing you have to remember is never to assume that the longest chain is always along the horizontal zigzag line. The longest chain can be anywhere. It can bend in the upward direction or in the downward direction and can lie along any path. So be careful with that. Here we have a chain which is given in this horizontal orientation. That chain need not be the longest chain, because there is another chain, another path that gives you more number of carbons. Let me tell you what I'm talking about. If I take this as the longest chain, it has 1, 2, 3, 4, 5, 6, 7, 8 carbons. Whereas if I take this horizontal chain as the longest chain, it has 1, 2, 3, 4, 5, 6, 7, only 7. So which has more number of carbons? The one that I numbered in blue. So which is to be taken as the longest chain? This chain. This chain is supposed to be taken as the longest chain, or the backbone of the compound, and this is to be considered as the substituent, and not this as the longest chain and this as the substituent. So the correct name of this compound is what? Let me see. So I'll erase this purple numbering because it's not the right one according to the chain length rule. So it has 8 carbons, that's why the name is octane, and there is only one substituent, that is methyl, and it's attached on carbon number 3, and it's written as 3-methyl because 3 is the locant. If I go to the next structure, this is the longest chain, which has how many carbons? 1, 2, 3, 4, 5, 6 carbons. Or I can take this as the longest chain also because it's identical, or I can take this as the longest chain also, or I can take this as the longest chain also because it too has 1, 2, 3, 4, 5, 6 carbons. But irrespective of any path among these 4 paths you choose, you will end up with the same name because all the 4 paths are exactly the same. They are not unique paths, they are similar paths. So it doesn't matter which path you choose, you'll end up with the same name. Now let me assign the locants to the longest chain and check for the lowest sum rule. Now if I write the numbers on all the carbons of the longest chain and check, you have a substituent here 2 and you have two substituents here, so I have to add it twice, 3 plus 3, plus you have one substituent here, so it's plus 4 and plus 5. So what is the sum? 4 plus 5 is 9, 9 plus 6 is 15, 15 plus 2 is 17 according to the blue numbering. Now according to the numbering from the opposite side, 1, 2, 3, 4, 5 and 6, what is the sum? So we have a substituent at 2, we have a substituent at 3, we have two substituents at 4 according to the purple numbering, so 4 plus 4, plus there is one substituent at 5. So what do you get here? You get 5 plus 4 is 9, 9 plus 4 is 13, 13 plus 3 is 16, 16 plus 2 is 18. So which is the right way of numbering? Is it the numbering written in blue or the numbering written in purple? Obviously it's the numbering written in blue because it gives you the lower sum, and the lowest sum rule should be obeyed. If I erase the purple numbers, what should be the name of the suffix? It's hexane because it has 6 carbons and there are 1, 2, 3, 4 methyl groups. That's why it's tetramethyl, and they are located at carbon 2 here, 2 of them at carbon 3, so I need to write 3, 3 explicitly, and then 1 at carbon 5. And there is an ethyl group at carbon 4 which gives you 4 ethyl here. Now I need to place or arrange these substituents in front of this suffix. So what do I decide on? I decide on the alphabetical order. In tetramethyl, what do I look at? Do I look at T or do I look at M? I look at M. And for ethyl I look at E. Anyway, E comes before M, so 4 ethyl is written first, and then 2, 3, 3, 5 tetramethyl hexane. That's what the name is. The next set of structures involves cyclic carbon chains or carbon rings. Now when we have rings of carbons attached to straight chains of carbons, irrespective of the lengths of the ring as well as the straight chains attached to it, the status of the parent chain always goes to the ring and not the straight chains, no matter how long the straight chain is. Even if a long chain is attached to a small ring takes the status of the parent chain or the main suffix. Let me explain with these examples. Here I have a 6-membered ring which is attached to a 2-carbon straight chain. Here the status of parent chain goes to the 6-membered ring, and here we have a 4-membered ring attached to 1, 2, 3, 4, 5 carbon straight chain. Here the straight chain is longer than the ring, but still the status of the parent chain goes to the ring, which is cyclobutane, and in the first structure it was cyclohexane. That means no matter how long the straight chain is, it is always given the status of a substituent and not the parent chain. The parent chain is always the ring or the cyclic part of the structure, no matter how small or how big it is. That's how the rule is. In this compound, we have a 6-membered ring, so the suffix becomes cyclohexane and it is attached to an ethyl group. So you have ethyl cyclohexane. Now observe that this is a cyclic compound, and that's why there is no numbering on the substituent, because the substituent can be attached to any carbon and all the carbons are identical. All the 6 carbons are on the ring and they are identical. Hence, whenever a single substituent is attached to a cyclic compound, it is always attached to carbon 1 if we can number it, and because it is always attached to carbon 1, we need not mention it because that would be a redundant information, so we don't give number. In the second case, we have a long straight chain with 1, 2, 3, 4, 5 carbons attached to a smaller ring with 1, 2, 3 and 4 carbons. and there is a single bond between the two structures. Now, what would be the name of this compound? Let's check. What do you think will take the status of parent chain? Is it the longer straight chain or the smaller ring? Even if the ring is smaller, it is always given the status of the parent chain, and hence the substituent is pentyl and the parent chain is cyclobutane. Hence the name cyclobutane with a substituent pentyl in front of it. That's the name of the compound, pentyl cyclobutane. Now let me go to the next structure. Now in the structure here, we have two substituents on the ring. Now this is your ring. It is a 6-membered ring, and there are two substituents. One is ethyl, another substituent is methyl. Now here, because they are attached on two carbons, they could be attached anywhere. So methyl can be attached here also instead of here. So the structure would be different. So here the necessity to number the carbons arises. Now how do I number? I number according to the lowest sum rule. So what do I mean by lowest sum rule? I cannot start numbering here. It's wrong because the sum of locants of the substituents is 3 plus 4, which is equal to 7. But instead I can number from here 1, 2, 3, 4, 5, 6. Here the sum of locants is 1 plus 2 equals to 3. So according to the lowest sum rule, this green numbering is correct rather than the blue numbering. Now the question is, how should I number? Should I number like this, or should I number like this? Again, this is a tie. In case of tie, what do? You look at the alphabetical order. The substituent which comes alphabetically first should get the lower number, and which comes second should get the higher number. So methyl group comes after ethyl alphabetically. So which should be given number 1, ethyl or methyl? Ethyl should be given number 1. So among these two, which numbering is correct? Blue numbering or green numbering? It's green numbering that is correct, because according to green numbering, 1 gets ethyl and 2 gets methyl. According to blue numbering, 1 gets methyl and 2 gets ethyl. So 1 should get ethyl and 2 must get methyl. And while writing the whole name, cyclohexane, the suffix is written, and in front of the suffix, first you write 1 ethyl because it comes alphabetically first, and then you write 2 methyl. So this is how the numbering is done for cyclic compounds. This next structure, let me see. Here we have a cyclohexane, and there are two substituents. One is here and the other is here. So how should I number it? I should start numbering either from here, or I should number starting from here, because these two numberings will give you the lowest sum, which is 1 plus 3 equals to 4. Now the question is, which is correct, the green one or the blue one? Here you have an isopropyl group. Here you have a methyl group. Now there is a tie here according to the lowest sum rule, so numbering should be done based on the alphabetical order. Now tell me which comes first, isopropyl or methyl? In isopropyl, I should consider I for the alphabetical order. I comes before M. So isopropyl should get the number 1 and methyl should get the number 3. So I think the blue numbering is correct. Your answer is 1 isopropyl, 3 methyl cyclohexane. Let me come to the next structure. Here you have a chain, and it's quite easy to identify which the longest chain is. It's the black chain, of course. Even if the color is not given differently, you can easily tell that this chain is the longest chain. How many carbons it has? 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. That's why the name nonane. Now let me look at the substituents one by one. If I look at the substituents, I have an isopropyl group and I have this group, which is 1, 2, 3, 4, a butyl group, and the secondary carbon is attached to the parent chain. That's why that becomes secondary butyl group. Now the question is how to number it. Should I number it from here? Or should I number it from here? So according to the lowest sum rule, if you look at the blue numbering, it's 6 plus 5, 11. And if you look at green numbering, it's 4 plus 5, it's 9. So which numbering is correct? Green numbering is correct because it gives you the lowest sum. So according to the green numbering, here is the suffix nonane because it has 9 carbons, and there is an isopropyl group at 4th carbon, and there is a secondary butyl group at 5th carbon. Now the question is, should I write this first or this first? I look at alphabetical order. So for isopropyl I look at I, and for secondary butyl I don't look at S but I look at B. Because secondary, tertiary, di, tri are not to be considered while looking at the alphabetical order. Only iso is considered. Rest of them are ignored. B comes before I, so secondary butyl comes before isopropyl. So that's why this name. Let me look at the next compound. In the next compound, if you see, the longest chain is this, which has 1, 2, 3, 4, 5, 6, 7, 8 carbons. And there is one more longest chain, which is this, which has 1, 2, 3, 4, 5, 6, 7, 8 carbons again. But why did I choose this black chain? Because if I choose this chain, it has only 2 substituents. But if I choose this chain, I have 1, 2, 3 substituents. So in case of a tie of 2 different paths, we have to choose the path which gives you more number of substituents, which is this black line. Now, after choosing the black line, how should I number? Let me start numbering here. 1, 2, 3, 4, 5, 6, 7, 8. So what's the name? It's octane because it has 8 carbons on the longest chain. And there is a methyl group on carbon 3, so it's 3-methyl written here. There is an isopropyl group at carbon 5. This is an isopropyl group, so 5 isopropyl is written. And then there is a normal propyl group at carbon 4, so it's 4-propyl. Now, how to arrange these substituents? Again, I have to look at the alphabetical order. So for isopropyl I look at I, for methyl I look at M, and for propyl I look at P. So I comes before M and M comes before P. So that's why the name is written this way. Let me go to the next slide. I'm introducing you to the functional groups. And here the functional group is a halide group. Now a functional group is something that gives you the nature of the compound, the way it reacts, and so on and so forth. In other words, a functional group defines the chemical nature of a molecule, and we'll be dealing with that when we look at the reactions of functional groups individually. But here we stick to the nomenclature. Whenever you have a halide as a functional group, the naming is done by writing halo in front of the suffix. For example, if you have chlorine, you write chloro, bromo for bromine, and iodo for iodine. That is how naming is done for halides. Now let me look at this first compound. So the carbon chain is this carbon chain. How many carbons it has? 1, 2, 3, 4, 5, 6 carbons, and chlorine is attached to the 6th carbon. Or is it attached to first carbon? It is attached to first carbon actually. I can number it from here. So I get substituent at 6, but I can also number it from here. Now chlorine is attached to first carbon. So which will you prefer? Again, you go by lowest sum rule, but here you don't have any sum, you have only one number, that itself is the sum. So which is it? Is it 1 which is lowest or 6 which is lowest? I think 1 is lower than 6, so this numbering is correct. That means numbering from the right is correct, not from the left. So that gives you the name of the compound, 1-chlorohexane. And here you have again 1, 2, 3, 4, 5, 6 carbons. Now this numbering is not correct, but this numbering is correct. Numbering from the left, I get substituted carbon 5, so this is the right way according to the lowest sum rule, hence the name 2-fluorohexane. Next, what about this? Now, by looking at the compound, I can just guess that the numbering from right gives you the lowest sum rather than numbering from the left, because I can roughly see that bromines are more towards right. So I number it from here 1, 2, 3, 4, 5, 6. So it's a hexane, and bromine is attached to carbon number 2 and carbon number 3. That gives you the name 2,3 dibromohexane. What about this? Is numbering from the left more probably right, or the numbering from the right? I think numbering from the left would be right, because iodines are looking more towards left. If you're not sure, you can just check both the ways of numbering, but here I can just guess that numbering from this side is better. So if I number from the left, I get 2 iodines at carbon number 3, but if I number from the right, I would get at carbon number 4. So this is correct. So that gives you the name 3,3 diiodohexane. What about here? Here you have 2 halogens, which are different, chlorine and iodine. And here the numbering from the left is probably correct, because they are looking more towards left. So it's 3-chloro, 3-ido. Now tell me, 3-chloro comes first in the name or 3-ido? I think 3-chloro comes first, because C comes before I alphabetically. So it's 3-chloro, 3-idohexane. What about this molecule? I have 3 substituents here. Now just a blind guess. If you just look at the compound and can give a conjecture from which side should I number, I think the numbering should be from left. 1, 2, 3, 4, 5, 6, rather than numbering from the right, which is 1, 2, 3, 4, 5, 6, because there are 2 substituents here and there is 1 substituent here. So it's better to number it from here, 3, 4, 5, 6. So what is the name? It's 3-chloro and 3-ido, because chlorine and iodine are attached to carbon number 3, and it's 4-fluoro. Now which comes first, second and third? Chloro comes before fluoro and fluoro comes before ido, because alphabetically C comes before F and F comes before I. So that's how the naming is done. What about this? So here I think numbering from left or right will give you the same name, because this molecule looks symmetric from the left and from the right. So either way you're going to end up with the same name. So either way you have fluorines attached at carbon 2, 3, 4 and 5. So the name is 2, 3, 4, 5 tetrafluoro, because there are 4, and it's hexane because total number of carbons are 6. What about this? 1, 2, 3, 4, 5, 6. This is the correct way of numbering, because iodines look more towards left. So the answer or the name of this compound is 3,3 diiodohexane. Let me go to the next slide. I think this compound is repeated here, so that was a mistake in the preparation of the slide. But anyway, let me go to the next slide. Here I have alcohols. Now alcohols are named as alls. That means their names end with all. Now to whichever carbon the OH group is attached is numbered here. So let me explain what I'm trying to say. Here you have a carbon chain with 1, 2, 3, 4, 5 carbons. So I can number it like this, or I can number it like this. Now if I number according to the blue color, the OH is attached on 5th carbon, and according to green it's attached at 1st carbon. Again the lowest sum rule holds good here, so this number should be as low as possible. So the green numbering is correct rather than blue. So the name of the compound is pentane because it has 5 carbons and it doesn't end with E, unlike alkanes which end with E. Here that E is replaced with OL, and between OL and the suffix, or I can say the name of the parent chain, the number is written. The number signifies to the number of carbon to which the OH group is attached, or it is the locant here. So here the numbering in green is correct, and the name becomes pentane 1-ol. And in the second structure, again the numbering should be done from the right rather than from the left, because OH is looking more towards right, so it's pentane 2-ol. And here you can number from either left or right, you'll get the same answer. So here you'll get pentane 3-ol here because OH is attached to which carbon? Carbon number 3. Is this first compound, is it primary alcohol, secondary alcohol, or tertiary alcohol? I think it's primary alcohol because OH is attached to a carbon which is primary. A primary carbon is a carbon which is attached to only one other carbon. What about this? Is it secondary alcohol, or primary alcohol, or tertiary alcohol? I think this is secondary alcohol because OH is attached to a secondary carbon. What is a secondary carbon? Secondary carbon is a carbon that is attached to 2 other carbons. And in the same way, this is also a secondary alcohol because carbon 3 is also a secondary carbon to which OH is attached. What about this next structure? Where should I start numbering? Should I start numbering from right or left? By now you should be able to guess which is the better side to start numbering from. So here, because the substituents look like they are attached more towards right, I start numbering from right. So it's 1, 2, 3, 4, 5. So it is a 5 carbon chain with 1 methyl group at carbon 2 and 1 OH group at carbon 1. So the name is pentane 1-ol because OH is on carbon 1, and 2-methyl because there is a methyl group on carbon 2. What about this? Here again I need to number from right rather than left because the substituents are looking more towards right. So it's 1, 2, 3, 4, 5. So there is a methyl group as well as OH attached on carbon 2. That's why the name is 2-methyl 2-pentane 2-methyl-pentane-2-ol. What about this? From which side should I number? 1, 2, 3, 4, 5. Is this correct? No, I don't think so. This is wrong. I need to number from right again because that gives me 2 plus 3 rather than 3 plus 4. 2 plus 3 is 5 and 3 plus 4 is 7. So 5 is lower than 7, so this numbering is correct. So according to this numbering, what the name of this compound is? The name is pentane 3-ol because OH is attached to carbon 3 and there is a methyl group on carbon 2. So that gives you the substituent 2-methyl. Now the question is, what kind of alcohol is the first compound? This compound. Is it primary, secondary, or tertiary? I think it's primary because OH is attached to primary carbon. This one is tertiary because OH is attached to a carbon which is tertiary carbon. A tertiary carbon is a carbon which is attached to 3 other carbons. What about this? This must be a secondary alcohol because this carbon is secondary and OH is attached to a secondary carbon. Fine. Next we come to amines. The name of amines end with amine, just like names of alcohols end with ol or ol. So here we have an amine group. So again, numbering should be easy by now. I should number from right again. So there is an amine group attached to carbon 1. That's why the name is pentane, because it is a 5 carbon ring. 1 amine because the amine group is attached at carbon number 1. Here the numbering should be done from the right again, because it is more towards right. NH2 group is attached more towards right. So what do you think the name of this compound is? It is pentane 2 amine. And here similarly you can number from either side, left or right, you'll get the same answer. So here your answer is pentane 3 amine. Now what do you think is the nature of these amines? Is this primary amine, secondary amine, or tertiary amine? It's primary amine. What do you think this amine is? Is it primary, secondary, or tertiary? If you answered secondary, then you're wrong. It's still a primary amine. Unlike alcohols, where you decide the nature of alcohol, primary, secondary, or tertiary, depending on the carbon to which the OH group is attached, an amine group, if it is NH2, it's always primary. If it's NH2, it's always primary. Let me explain what I'm talking about. If nitrogen is attached to 2 carbons, then it becomes secondary, like in this compound. And if nitrogen is attached to 3 carbons, then it becomes tertiary. So the definition of how we define primary, secondary, and tertiary in alcohols is different than the way in which we decide primary, tertiary, and secondary for amines. That you need to just remember. Now let me come to the next compound. Here again, where do you do the numbering from? Right or left? I think from right again. So 1, 2, 3, 4, 5. So it's pentane, and amine is attached to carbon 1, so it's pentane 1 amine. And there is a methyl group here. I didn't write that in red, I forgot. So there is a methyl group here, so it's on carbon 2, that's why there is 2 methyl here. Next, here again the numbering is like this. 1, let me write in blue, 1, 2, 3, 4, 5, the longest chain. Now there is a methyl group as well as amine group attached to carbon 2, that's why the name is pentane 2 amine, and there is 2 methyl in the front of the name. Whereas this you can number either from left or right. So it's pentane 3 amine. What about this? I number from here. So I get 2 methyl because there is a methyl group on carbon 2, and pentane 1 amine because amine group is at carbon 1. Now look at the next compound. There are 2 methyl groups attached to nitrogen. So when I have this kind of compound, what do? I look at the longest chain. So this is the longest chain, carbon chain. Let me show you what the longest chain is. This is the longest chain. So that becomes the parent chain. So it has 3 carbons, whereas this side has 1 carbon and this side also has 1 carbon. So that is not considered as the longest chain, that is considered as substituent. That's why I have written that in red or drawn that in red. So this is 1, 2, 3 carbon. That's why the main name is propane, because it has 3 carbons. And on that main chain, the nitrogen is attached to carbon 1, because if I number it, I can number it from right rather than left, because if I number it from left, you'll get nitrogen attached at carbon 3. So according to the lowest sum rule, this is the right way of numbering. So it is propane 1 amine, and there are 2 methyl groups attached to nitrogen rather than until now we have seen methyl groups attached to carbon chain on carbons. Here the situation is different. The methyl groups are attached to nitrogen. So what do? We write the locant as N and N here, not like giving it a number, but instead of giving it a number, we give it the name N, which signifies that the substituent is attached to nitrogen. So that is actually the address of the substituent. So in this case, we don't have carbons to which the substituents are attached, but there is only one nitrogen to which the substituent is attached, and we can give it the address as N, or the locant can be denoted by letter N. So that's why the name is N, N dimethyl, because there are two methyl groups, and hence this name, N, N dimethyl propane 1 amine. Similarly, if you look at the next compound, which is the longest chain, which is the longest continuous carbon chain. This is the longest continuous carbon chain, which has 4 carbons. So how should I number it? Should I number it from here, or should I number it from here? I think the green numbering is correct, because the substituent is coming on carbon 2 rather than carbon 3. So this is correct. Here you get it carbon 3, which is wrong, because it violates the lowest sum rule. So I number it according to the green color. And what group is attached to the second carbon? So amine group is attached. That's why the name is butane, because it has 4 carbons on the longest chain. And amine group is attached to second carbon. That's why it's butane 2 amine. And there is another substituent, a methyl group. Here a methyl group attached to nitrogen. That's why the methyl is written here, the substituent, and its address is N, the locant is N, and not a number, because the methyl group is not attached to the carbon chain, but rather it's attached to nitrogen. So this is how the naming is done. Now here, if you see, as I mentioned before, this is a secondary amine because there are 2 carbons attached to nitrogen, and this is a tertiary amine because there are 3 carbons attached to nitrogen, and this is a primary amine because there is only 1 carbon attached to nitrogen. So that's how the distinction between primary, secondary and tertiary amines is made. Whereas in case of alcohols, you always have OH, and you see to which carbon is OH attached to decide whether it is primary, secondary or tertiary. So let me go to the next slide. So here we are coming to acids. Now an acid group is a COOH group. Now this group, if you condense and write, you can write it as COOH. This is a COOH group, and this is a COOH group. Now until now, what did you see? Until now we saw that halides, alcohols and amines were not part of the parent chain, because the parent chain is always composed of carbons, because alcohols, amines and halides do not contain carbon. They cannot be the part of the parent chain. They are attached to the parent chain from outside. So the parent chain has these locants or numbers allocated to each carbon, and to one of those carbons these functional groups are attached. The functional groups of halogens, alcohols and amines. So these functional groups cannot be the part of the chain. That means they cannot hold any locant, or they cannot be allocated any number because they are not carbon. But whenever we have functional groups that have carbon in them, the carbon in the functional groups should be the part of the parent chain and has to be given the lowest number, or the locant on the carbonyl carbon. For example, in acids and aldehydes and ketones should get the lowest possible number. And if the functional groups are like acid and aldehyde, the carbonyl carbon should always get the number 1. That means the chain must start at this carbonyl carbon. And you know what a carbonyl carbon is? A carbonyl carbon is any carbon that is attached to an oxygen atom by a double bond. So we have carbonyl carbons in functional groups of acids, acid derivatives and aldehydes and ketones. But in the case of aldehydes and ketones, you have to get the carbonyl carbon at the end of the chain, and it should be preferably given the number 1. If there is only one carbonyl carbon, it must get number 1. If there are 2 then it may get some other number, the second carbonyl carbon, but at least one of the carbonyl carbons should get the number 1. There is a special case at the end we'll discuss. Now let me start. Let me explain what I'm trying to say. Here you have this structure, first structure. Now I don't start numbering from here and consider this to be a substituent, but rather the correct way of numbering is you start with the carbonyl carbon in case of acids, and you give it number 1 preferably, even if it violates the lowest sum rule sometimes. Let me explain what I'm trying to say. So this is how you number this compound, and here there are no substituents at all, so the name of this compound is hexanoic acid. So acids, names of the acids end with oic acid. So if you have 6 carbons, it's hexanoic acid. If you have 7 carbons, it's heptanoic acid. If you have 5 carbons, it's pentanoic acid. And 1 carbon is methanoic, 2 carbons ethanoic, and so on and so forth. Now let me look at the second structure. If you look at the structure, there is a carbonyl carbon at the bottom. So I'll start numbering there. 1, 2. Should I go here or should I go to the left? So if I go to the right, the chain will become short, so that will not be the longest chain. So I'll go to the left. So it's 3, 4, 5. So you have 5 carbons, that's why it's pentanoic acid. And to the carbon 2, you have a methyl group attached, that's why we have 2-methyl. What about this third structure? I'll start numbering here. 1, 2. I can go to the right or left, it doesn't matter. I'll get the same thing because it's symmetric from here. The path is symmetric. So I'll go 3, 4. So it's 4 carbon chain, that's why it's butanoic acid. And there is an ethyl group attached to carbon 2, that's why it's 2-ethyl butanoic acid. Similarly, when you have aldehydes, what do you have? You start from carbonyl carbon, so it's hexanal. What about this? You have 2-methyl pentanal. See, unlike alcohol where the name ends with OL, here names ends with AL. So this is for aldehydes and this is for alcohols. But when someone says the names, they sound quite similar, but if you stress it well enough, you can make a distinction. So for example, 6-membered alcohol is called hexanol and an aldehyde is called hexanal. Anyway, what about this? 2, 3, 4. I can name it to the right also. I'll get the same name. So it's 2-ethyl butanol. Now let me stress one more thing. So if you have this COOH, the structure like this, and you have a substituent here and a substituent here and a substituent here, if you start numbering from here, 1, 2, 3, 4, 5, 6, 7, 8, what is the sum of the substituents or the locants of the substituents? It's 5 plus 6 plus 7, which is I think 11 plus 7, which is 18. But if I number it from the other end, let me do it in purple. 1, 2, 3, 4, 5, 6, 7, 8. What will be the sum? The sum is 2 plus 3 plus 4, right? So 2 plus 3 plus 4 is how much? It's 7 plus 2, 9. But the thing is, even if this gives you the lowest sum, this is the wrong way of numbering, and the red numbering is the right way. The red numbering is the right way, because even if you violate the lowest sum rule, the rule overriding that rule is that the carbonyl carbon in case of acids and aldehydes should always get the number 1. It should always get the number 1. Okay. Whenever the situation demands. So we have to just override the lowest sum rule. So let me go to the next structure. What happens if you have 2 COOH groups? you have two COH groups on the same molecule. So what you do is, in case of having two COH groups, you start at either of the group and you start numbering it: 3, 4, 5, 6, 7, 8, 9, 10, 11. You have 11 carbons in total. If you start numbering from one carbonyl carbon and end your numbering at the other carbonyl carbon, that's why it's undecane. It's undecane, and because it has two acid groups, it's called dioic acid. If it has only one acid group, it's called just an oic acid, but it has two, that's why it's called dioic acid. Now in this case, you have to consider the carbonyl carbons while numbering and giving the parent chain, name to the parent chain. But what if you have three COH groups? When you have three COH groups, the rule is that you do not consider carbonyl carbons while numbering. You just consider the chain to which more than two COH groups are attached. Here we have three, that's why numbering is done from here: 1, 2, 3, 4, 5, 6, 7, 8, 9. You know why this rule exists? Because if you start numbering from this carbon and end at this carbon, this carbonyl carbon, you will miss this carbon, right? But in the previous case, that was not the issue, right? If you start at this carbon, you will end up at this carbon, and you would be numbering both the carbonyl carbons, or you would be taking both the carbonyl carbons into consideration while giving them numbers. But when you have more than two COH groups, you cannot start at one carbonyl carbon and end at the other without missing the other COH groups apart from those two. So here, if I start numbering from here and end it here, I'll miss this. Or if I start numbering from here and end it here, I will miss this. So either way, I will have to miss one of the carbonyl carbons if I start numbering them or giving them numbers. So rather than that, they decided that if there are more than two COH groups, you don't number the carbonyl carbons, you just number the carbon chain to which these COH groups are attached. More than two COH groups are attached, and here in this case we have 9, right? So that's why the name is what? Nonane, and not undecane, it's nonane. After giving the numbers appropriately, on which carbons are the COOH groups attached? They are attached on carbon 1, carbon 5 and carbon 9. That's why the name is 1, 5, 9 tricarboxylic acid. That gives the name of this compound. The same principles are followed for naming an aldehyde. Here we have total number of 11 carbons. That's why the name is undecane, and because there are two aldehyde groups, it's undecane diol. The name is undecane diol. Now in the situation where I have more than two carbonyl groups or two aldehyde groups attached to a molecule as shown here, I cannot take any two as the part of parent chain because I will miss the third one. So instead, what do? I consider only the rest of the chain as parent chain, and I'll consider all three as substituents. So we have total number of 9 carbons here. That's why the name nonane, and the carbonyl carbons are attached, or the aldehyde groups are attached on carbons 1, 5 and 9. That's why the name is 1,5,9 tricarbaldehyde. So that's how the naming is done for aldehyde, where we have more than two aldehyde groups, just like in the case of carboxylic acid. It's the same situation here. Now let me go to the next slide. So the next slide, we have alkenes here. When we have alkene as our functional group, we give numbering to the parent chain such that the alkene or the functional group gets the lowest possible number, irrespective of the lowest sum rule. So here I start numbering from the right because the double bond is towards right, and the double bond lies between carbon 1 and carbon 2. So I'll take the lower of the two numbers, which is 1. So the name is hex because there are 6 carbons, and 1 ene because the double bond lies between carbon 1 and carbon 2. And I have to take the lower of the two numbers, so it's here, 1. Obviously, the double bond looks more towards right, so I start numbering from right. So the double bond sits between carbon 2 and 3, so take the lower number 2. So that's why the name is hex 2-ene. And this E represents the geometric isomerism, which I'll discuss later. There are two, E and Z. So there is a hydrogen attached here and there is a hydrogen attached here, which is invisible to you. So the heavy groups are on the opposite side, like trans. So it's given notation E. If they are on the same side, it's given notation Z or Z. I'll discuss about that later when I discuss geometric isomerism. It's a big topic again. It deserves the lecture of its own. What about the next compound? So if I number it 1, 2, 3, 4, 5, 6, and I can number from the other end too, but it will give you the same result because 2, 3, 4, 5, 6. Either way, you'll get the same answer, red or purple. So the double bond is sitting between carbon 3 and carbon 4. So I'll take the lower number. That's why it's hex 3-ene. And E again represents the geometry. Now this is called a terminal alkene because the double bond is present at the end of the chain. These two are called internal alkenes. Anyway, what about this? Again, I number from here. So we have a 6 carbon chain, which is the longest chain, with a methyl group attached at carbon 5. So the double bond lies between carbon 1 and carbon 2. That's why it's 1-ene. And because the methyl group is attached to carbon 5, it's 5-methyl hex 1-ene. That's the name of this compound. What about this next compound? Again, I number from here. So the name is hex 1-ene because it's sitting between 1 and 2. So I take the lower number. And there are 2 methyl groups attached at carbon 4 and carbon 5. So that gives me the name 4,5 dimethyl. Similarly here, you get hex 1-ene again because it is same. And there are 3 methyl groups attached at carbon 2, 4 and 5. 2, 4 and 5. So you have 2, 4, 5 trimethyl hex 1-ene. And here, there is a structure that is of different geometry. Here you had a hydrogen attached here and a hydrogen attached here, and the heavier groups were attached on the opposite sides. So that was E, but here a hydrogen is here and a hydrogen is here, which is invisible. So this is a hydrogen here, hydrogen here. So the heavier groups are attached on the same side. That's why the Z configuration. Here also the Z configuration because the hydrogens are here, and same way here. Anyway, the names. What are the names? So where should I start numbering from the left or right? So it's quite clear that it's better to start numbering from left because the double bond looks more towards left and it's between carbon 2 and 3. So I choose the lower number, so it's hex 2-ene. What about this? This has 4 carbons, so I can number from the either side. I'll get the same answer because it is symmetric. So it sits between carbon 3 and 2. So I take the lower number, so it's but2-ene. Similarly, this is 1, 2, 3, 4, 5, 6. I can number from either side. I'll get the same answer. And it sits between 3 and 4. I take the lower number. That's why it's hex 3-ene. Now let's come to the alkynes. The naming of alkynes is also quite same as in the case of alkenes. But instead of ene, you get the name ine. So here it is symmetric, so I can number from any side. So it is 4 carbon. So it's but, and the triple bond is between 3 and 2. I take the lower number, so it's but2-ine. Here I start numbering from here. So this is 1 carbon and this is another carbon. Notice that there is no bend at the carbon 2 because it is sp hybridized, because it is at the end of a triple bond. Unlike in the case of carbons which are at the end of double bonds where you have a bend, because at the end of double bond you have a carbon which is sp2 hybridized, which has a bond angle of 120 degrees and not 180 degrees. So make sure when you have a triple bond, at the end of triple bond there is a carbon there. You need to make the distinction. Even though there is no bend in the structure there is a carbon there, so there is carbon 1, 2 and 3 here, so you need to keep that in mind. Anyway, the name of this compound is butanine because the triple bond is between carbon 1 and carbon 2. And here again I can number from the either side, so it's between 3 and 4. I take the lower number, so it's 3 ine and total number of carbons are 6, that's why it's X. In case of cyclic alkenes, it has a rule of its own. In the situations where there is only one substituent attached to one of the double bonded carbons, it is supposed to get number 1 as its locant, irrespective of the lowest sum rule. If there are two substituents attached on both the double bonded carbons, then you can go with the lowest sum rule. But if there is only one substituent attached to one side of the double bond, then the carbon to which the substituent is attached is supposed to get number 1. We'll see in the following examples what I mean to say. So we have certain molecules given, and in these molecules, one of the molecule illustrates the rule that I just talked about. Let's see. In the first structure, the name of the structure is written as cyclohexene and there is no numbering there. Even if you number 1 and 2, it would be one cyclohexene, but there is only one kind of cyclohexene possible. That would be one cyclohexene, and writing 1 is redundant. That's why writing 1 doesn't make any sense. So the name is just cyclohexene. Now the second structure. In the second structure, you have a methyl group attached. Now where will you start numbering? You can start numbering here, or you can start numbering here. Now why is numbering important here? Because the methyl group which is attached could be anywhere. It could be here, it could be here, it could be here, or it could be here, and all these compounds are different so we need numbering in this case. Unlike the last case where there was no numbering required, it was obvious that there is only one cyclohexene that you can draw, but methyl cyclohexene you can draw several, so I need to number. So I can start numbering here, or I can start numbering as shown in green. So according to the lowest sum rule, the purple numbering is correct because the substituent is coming on carbon 1 rather than coming on carbon 2. And the name of this compound is 1-methyl cyclohexene. In this next structure, where do you think the numbering must start? Should it start here, or should it be like this as shown in purple? 1, 2, 3, 4, 5, 6. So which numbering is correct? What do you think, the green numbering or the purple numbering? Now if you look at green numbering, the sum of locants is 2 plus 6, which is how much? 8. And according to the purple, it's 1 plus 3, which is equal to 4. So which do you prefer? You must prefer 4, so the purple numbering is correct. So what is the name of this compound? The name of this compound is 1,3. The purple numbering is correct, right? So a methyl group is at carbon 1 according to the purple numbering, and carbon 3. So it's 1,3 dimethyl, because both are methyl groups, cyclohexene. So here you followed the lowest sum rule. Good enough. Let me come to the next structure. So here, which is the better way to number, which is the correct way to number? 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. So obviously blue numbering is correct because the substituent is coming at carbon 3 rather than purple where it is coming on carbon 6. So the answer is, according to the blue numbering, which is 3-methyl cyclohexene. Here comes the part where you need to be careful. In the next structure, if I start numbering according to this purple color, if I number it like this, 1, 2, 3, 4, 5, 6, what does the sum of locants turn out to be? It's a 2, one methyl group is at carbon 2, another is at carbon 3, which is equal to 5. what about this blue numbering? 1, 2, 3, 4, 5, 6. According to the blue numbering, the sum of locants is 1 plus 6, which is equal to 7. But it turns out that this blue numbering is correct and purple numbering is wrong. Now, why is this situation arriving? Even if the purple numbering is giving you the lowest sum and the blue not. Blue is correct and purple is wrong. Because when you have a substituent on one of the carbon that shares the double bond, it must get number 1 or the locant 1. And the second thing is, irrespective of everything, number 1 and number 2 should be given to the two carbons on the either side of the double bond. That is very, very important. You look at all the structures, 1 and 2 are given to the carbons that contain the double bond. So the thing is, when you have a substituent on one of the carbons, that must get number 1. That is the first thing to note. And the second thing to note is the other carbon which is attached to the double bond gets number 2. So if you have no substituent attached to the either of the carbon sharing double bond, then you go by the lowest sum rule. But if one of the carbon has a substituent, it must get number 1 irrespective of the lowest sum rule. That means this rule overrides the lowest sum rule. So that is what you need to keep in mind while giving name for a cyclic alkene. And one more thing I need to tell you is that these names are not written by me. These are all computer generated names, so there is no mistake in any of the names given below the structures. So I didn't just check the structures and write the names manually. These are the names that are generated according to the programs written by IUPAC Nomenclature. So I have just drawn the structures and the computer just gave me the names. So these names are all correct, so you need not worry. In the next case, here if I number according to blue, what is the sum? It's 1 plus 2 plus 6, which is how much? 8 plus 1, 9. So if I start numbering from here, 2, 3, 4, 5, 6. According to the purple numbering, what is the sum of locants? It's 1 plus 2 plus 3, which is equal to 6. There is a substituent here and there is a substituent here. So either way, one of the carbons which has substituent attached gets number 1 anyway. So even in blue numbering and purple numbering, we have locant 1 on the double bonded carbon with substituent, unlike here. In the previous structure, if you do numbering according to purple, the carbon 1 was not getting the substituent, so purple was wrong and blue was correct because according to blue numbering there was a substituent at carbon 1. But here we don't have that problem. We have methyl group on both the carbons, so here we go by the lowest sum rule, which is 6 here. So the purple numbering is correct, and according to the purple numbering, what is the name of the compound? It's trimethyl cyclohexanone, because there are 3 methyl groups and the numbers are 1, 2, 3, not 1, 2, 6. So the purple numbering is correct. So let me go to the next slide. So here we come to ethers. Whenever we have ethers, we consider one of the alkoxy group as a substituent. Let me explain how do we name ethers. Let's proceed with the structures. Here you have this ether to which there is a methoxy group attached, because OCH3 is methoxy, which is attached to this long chain which has 1, 2, 3, 4 carbons. So it's butane, and on butane we have a methoxy group attached. And to which carbon is it attached? Let me start numbering. So if I number from this side, according to the purple color, this methoxy group is attached to carbon 4. But if I number from this side, this methoxy group is attached to carbon 1. So according to the lowest sum rule, the blue numbering is correct. That's why we get the name 1-methoxybutane. What about here? Here you have two parts, this part and this part. So the left part has 3 carbons and the right part has 2 carbons, so this should be taken as the substituent. So it's 1, 2, 3 carbons, so I'll number from here for lowest sum rule. So it's 1-ethoxy because this is ethoxy group. Ethoxy group is attached to the parent chain, so it's 1-ethoxypropane. What about this? This is again 1-ethoxypropane. It's just flipped because you have 2 carbons on the left side and 3 carbons on the right side, but it's actually the same structure, which is just flipped left to right. So it's again, this is the longest chain, so I number it 1, 2, 3. So this ethoxy group is attached to carbon 1 on the longest chain, so it's 1-ethoxypropane. And next we come to ketones. Now in ketones you have a carbonyl group just like we have had in aldehydes, but in aldehydes the carbonyl group was at the end of the chain, or wherever the CHO group was, that was taken as the end of the chain, and the numbering always started from that carbon in aldehydes. But because in ketones the carbonyl carbon sits in between the chain, therefore in ketone the carbonyl carbon sits in between the parent chain and gets the lowest possible number, but not 1. We get 1 in aldehyde, not in ketones. Now let me look at the structure given and try to name the structure. If I try numbering the structure from the left, or if I number the structure from the right alternatively in the blue color, I must choose the numbering which gives my carbonyl carbon the lowest number, because the functional group should get the lowest number. That is the rule. So the blue is correct and the green is wrong, and according to the blue, the name of the compound is hexane 2-one. All the ketones end with -one, and the carbonyl carbon, wherever it sits, gives the number that comes before -one, so it's hexane 2-one. If I go to the next structure and give it its numbering from left and from right, the right one seems correct because it gives the carbonyl carbon number 3 rather than 4, and I should go with the lowest possible number for carbonyl carbon, so the name is hex 3-one. And here you start numbering from the left. It's again hexane 3-one, so it's actually the same structure, it's just flipped from left to right. Now next comes acid chlorides. So these are the derivatives of acids. So OH group is replaced by a halide as shown here. The name of acid halides is given by oil chloride or oil iodide or oil bromide, depending on whether chlorine is present here, bromine is present here, or iodine is present here. So it has how many carbons? 1, 2, 3, 4, 5. So that's why it's pentanoyl chloride. And if there was iodine present here, it would be named pentanoyl iodide. And if it was bromine present here, it would be named pentanoyl bromide. What about the next structure? Let's proceed to the next structure. Is this an acid chloride? It's not an acid chloride, it's actually an aldehyde. So I start numbering from carbonyl carbon, because in aldehydes and acids I always start numbering from carbonyl carbon. 5 carbons, that's why it's pentanal. Chlorine is attached to carbon 2, that's why it's 2-chloropentanal, and this is 3-chloropentanal. If you look at these two compounds, these are actually positional isomers because the position of chlorine is different. But if you consider these two compounds, these two are functional isomers, but I will go into isomerism later. That's a big topic, that's a huge topic, and we need a detailed discussion on the isomerism, so I'll go to that later. So next we come to amides. Amides are also the derivatives of acids, in which the OH group is replaced by NH2 group, and their names are the names ending with amide. So if you have 5 carbons, 1, 2, 3, 4, 5, it's pentanamide. If you had 4, it would have been butanamide, and if you had only 2, it would have been ethanamide. Fine. What about this? This is again an amide. I'm again numbering it, starting from carbonyl carbon. So it is five carbon chain, so the name is pentanamide, and there are two methyl groups, these red color groups attached to it, that's why you have dimethyl, and one methyl group is at carbon 3, that's why you have 3 here and you have N here. You write N comma 3. You first write down the alphabets like N, and then you write the numbers like 1, 2, 3 in the order. So first comes the letters, then comes numbers in order. So here again it's same, it's 1, 2, 3, 4, 5 carbons, so it's pentanamide again, and there are 3 methyl groups, 1 methyl group, 2 methyl groups and 3 methyl groups. 2 of them are attached on nitrogen, that's why N comma N, and 1 is attached at carbon 3, that's why 3. So it is N comma 3 trimethyl pentanamide, and these are anhydrates. This is called acetic anhydride, or it is also called ethanoic anhydride. Why? Because it is formed by the condensation reaction involving 2 ethanoic acids. So if you have 2 ethanoic acids, this is one ethanoic acid, this is another ethanoic acid, so there is a condensation reaction, so this H2O goes off, so this is the oxygen here, and it is formed by the condensation of 2 ethanoic acids, that's why it's called ethanoic anhydride. And this is formed by 1 ethanoic acid this side and 1 propanoic acid this side, because it has 3 carbons, 1, 2, 3, and it has 2 carbons, ethanoic acid, that's why it's called ethanoic propanoic anhydride. It is also called acetic because it's the common name, so it is ethanoic propanoic anhydride. Fine. What about this? This came from ethanoic acid, and this came from some other acid. So let me see what acid that is. So you'll have ethanoic here instead of acetic. You can write acetic also, and you have butanoic acid on this side with a methyl group on carbon 2. That's why it's 2-methyl butanoic acid. So it is formed from ethanoic acid and 2-methyl butanoic acid. That's why it's called ethanoic 2-methyl butanoic anhydride. Fine. What about this? These are esters. These are also acid derivatives. And when you remove the acidic hydrogen from an acid and attach an alkyl group in its place, it becomes an ester. Here we have an alkyl group, methyl group in this case, a methyl group. Now how to name this? Here we have an ethyl group, and here also we have an ethyl group in place of hydrogen where it was an acid. Now if you look at this structure, we have 2 parts. One, the alkyl group which replaced hydrogen from the acid, and 2, the rest of the part which was the conjugate base of the acid from which it is formed. Now here we have a methyl group, and the rest of the structure is the conjugate base of propanoic acid, so that's called propanoate. So it is called methyl propanoate. That's how the naming is done, methyl propanoate. Let's look at the next structure. There is an ethyl group attached, 2 carbon, so it is ethyl, and the name is acetate here, but it's also written as ethanoate. Okay, it's also called ethanoate. And here you have ethyl group attached here, and here formate is written because this side is derived from formic acid, but it is also called methanoic acid, so it is also called methanoate. So this is ethanoate. Okay, this is methanoate. Anyway, this is how esters are named. Let me go to the next slide. What if the molecule is polyfunctional? That is, if more than one functional group is present in the same molecule, only one of the functional group takes the status of functional group, and rest of the functional groups are given the status of substituents. And the functional group is chosen according to the priorities given in the following table. So if the functional group has the higher priority or ranking here, it gets the status of the functional group, and the rest of the functional groups get the status of substituents in the molecule. For example, if you have an acid and alcohol both present in the same molecule, then the functional group is acid and OH becomes the substituent. I'll give you one more example with blue. If nitrile group is present as well as a ketone, then nitrile becomes the functional group and ketone becomes the substituent. That's how it's done. And when the functional groups become substituents, their names change and they are given as prefixes as shown in the table. Let me explain. For example, if ketone is considered as a substituent, it gets the name oxo as a prefix. If alcohol group is considered as substituent, it's called hydroxy. So let me explain you with the help of certain examples how the naming is done so that you'll get more clear picture. Okay, let me go to the next slide. So here you have two functional groups here. You have alkene functional group as well as alkyne functional group. These are called polyfunctional compounds. If you have alkene and alkyne, it's quite simple. So you start numbering. So where will you start numbering? Will you start numbering here according to the red, or will you start numbering here? When alkene and alkyne are present, both are present, alkene is preferred over alkyne. So functional group should get the lower number. If I number according to red, it would be giving preference to alkene, and if I number according to blue, it is giving preference to alkyne. We know that while considering the principal functional group, the higher priority is for alkene. So the red numbering is correct. That's why the name becomes but1ene and 3-ine. And in the next compound, we have acid as well as alkene. So here we start numbering always from carbonyl carbon. But the name is but2ene because the double bond lies between carbon 2 and carbon 3. So the name is but2enoic acid. That's how the naming is done. What about this? You have a nitrile group as well as an alcohol. So we know that nitrile group has higher priority over alcohol. We have seen in the table here. The nitrile group has priority over alcohol. So alcohol becomes the substituent. So the name of this compound is, you number from here. After numbering, you get total number of 4 carbons. That's why the name butane. And because it is a nitrile functional group, the name ends with nitrile. That's why the name butane nitrile. And on the carbon 3, you have OH group attached, which is now a substituent. That's why we have 3-hydroxy. That's the name given here. Fine. What about here? There is an amine group here. So if amine group is considered as a functional group, the name always ends with amine, like ethanamine, butanamine, pentanamine. But here, that loses the status of functional group and it becomes a substituent because nitrile is preferred. So it becomes a substituent, and when you are considering NH2 as substituent, you call it amino. So it is on 1, 2, 3, 4, third carbon. So it's 3-amino butane nitrile. What about this? When you have a nitrile group as well as an acid, let us go back to the table. So acid is always preferred over nitrile. Acid takes the status of functional group and nitrile becomes substituent. So let me number 1, 2, 3, 4. So it's butanoic acid because it has 4 carbons, and there is a CN group attached to third carbon. And when you have a CN group as a substituent, it's called a cyano group. So that's why it's 3-cyanobutanoic acid. What about this? Here you have an aldehyde group here and acid group, and acid is always given the first priority. So 1, 2, 3, 4, and whenever you have a double bond O present, it's always called oxo, both in ketone as well as in aldehyde. That's why it's 3-oxo because it's on third carbon. And it's what? How many carbons do we have? We don't have 4. I made a mistake. That's a hydrogen there. So there are only 3 carbons. So that's why it's propanoic acid. What about this? It has ketone and acid. So I number it 1, 2, 3, 4. Now I should consider this as carbon 4 because here there was hydrogen and here there is carbon. So there are 4. That's why it's butanoic acid. And there is an oxo group on carbon 3. So it's 3-oxobutanoic acid. What about this? There is an SH group here. So it's an acid again, 1 2 3 4. I intentionally took all the acids because they always take the preference. So I just wanted to show you how the different groups are called when they are considered as substituents. So here we have 4 carbons, that's why it's butanoic acid, and we have SH group attached on carbon 3, and SH group is called mercapto group. So it's 3-mercaptobutanoic acid. So it's just like alcohol, but instead of O you have S. It's also called a thiol. Okay. Anyway, what about this? Here you have acid again. I number it 1 2 3, and there are 2 groups attached here. This is just like acid chloride, but I consider these 2 groups as 2 substituents now, not a functional group. That's why there is an oxo group as well as chloro group on carbon 3. So it is 3-chloro 3-oxo propanoic acid because it has 3 carbons. What about this? Now you have an amide functional group here and acid is always preferred. So I write numbering from the carbonyl carbon of acid. So it has total number 3 carbons. That makes it propanoic acid, and there are 2 different groups attached. Now I'm not considering it as a functional group, but I'm considering them as substituents, so I'll take them separately. I'll take NH2 group separately, and I'll take double bonded O group separately. That's why it's 3-amino for this part and 3-oxo for this part. So the name becomes 3-amino 3-oxo-propanoic acid. Okay. Now here are some other compounds given. You can pause the video and just look at these names. Some of the names are common names here: benzoic acid, toluene, benzaldehyde, aniline, nitrobenzene. Toluene is given twice. I intended to give some other compound, I guess there. I forgot. But anyway, what about this compound? For choosing the parent chain, I have to choose the longest chain with highest number of substituents. So it's this. And after numbering, starting from carbonyl carbon, what would be the name of this compound? Let's check. It has 2 substituents, 1 phenyl and 1 methyl. And because it has 4 carbons, it's butanoic acid. And there is a methyl group at carbon 3, that's why it's 3-methyl. And a phenyl group at carbon 4, that's why it's 4-phenyl. And M comes before P, that's why this comes before this. Anyway, what about this? 1 2 3 4, and on carbon 3 there is a phenyl group, and there are 4 carbons, that's why it's butanoic acid again. Now in the neighboring structure there is a benzene ring, but there is no acid group like in this compound. So the acid group is absent in the neighboring structure. So the functional group becomes benzene, so the name ends with benzene. So the name of the compound ends with benzene, and to whatever group that is attached is written in front of it. So here a butyl group is attached, 1 2 3 4 carbons, that's why it's butyl benzene. And here you have a butyl group attached, but on the butyl group there is a methyl group. So you start numbering at the carbon to which the ring is attached. So 1 2 3 4, and it's attached on carbon number 2, that's why it's 2-methyl butyl benzene. Whereas this is the longest chain here, it's pentane. If I give locants to all the carbons on the longest chain, the phenyl group lies on carbon 2. That's why the name of this compound is pentane 2-yl benzene. That's how these compounds are named. So anyway, these are not as important as the compounds we discussed earlier, but anyway, I wanted to cover all the compounds, that's why I'm mentioning these 2. Next, let me come to the bicyclic compounds. Bicyclic compounds are quite interesting. Before giving the names to these bicyclic compounds, the first thing you will need to do is to find the bridgehead carbons. If you look at all these structures, there are 2 special carbons in all the structures given. The speciality of those carbons is that those carbons are bonded to 3 other carbons. Those carbons are called bridgehead carbons. If you see closely, there are only 2 bridgehead carbons in each and every compound. Let me explain. Unless or otherwise there is a substituent attached, there will be 2 carbons which are bridgehead carbons because they are attached to 3 carbons each. And there is a bridge on the bridgehead carbons, that's why the name bridgehead carbons. Now, how to identify the bridgehead carbons? It's quite easy. Look at the carbons which are attached to 3 edges, which have 3 edges, and look at all the rest of the carbons, they have only 2 edges. That is how we identify the bridgehead carbons. After identifying the bridgehead carbons, we now look at all the bridges attached to the bridgehead carbons. There are 3 bridges, and now we count the number of carbons on each bridge. On the left, we have 2 carbons. On the right, we have 2 carbons again, is green, and on the top bridge, you have only 1 carbon, 1 purple bridge. After identifying number of carbons on each bridge attached to the bridgehead carbons, we write the name of the compound. So how to write? Let me tell you. So what we do is, we open the square bracket and write the numbers of carbons on the bridges in decreasing order. So we have 3 bridges here with 2 carbons, 2 carbons and 1 carbon. So let me write in the appropriate colors. So first we have 2 green carbons, you write dot, and then 2 blue carbons and then dot, and there is 1 purple carbon. So this is in decreasing order. I write purple carbon, I close the bracket, and now I count all the total number of carbons present in the structure. So these are carbons on the bridges plus 2 bridgehead carbons. So the total number of carbons on the bridges are 2 plus 2 plus 1, which is how much? 5, plus 2 bridgehead, which is 7. So that gives us the name heptane, because it is a structure with 7 carbons. And in front of the square bracket, you need to write Bicyclo, which represents that this is a Bicyclo compound to start with. This is how the naming is done. Let's proceed with the other structures. What about the next structure? Let us see. Let us apply the same principle. We first identify the bridgehead carbons, these red carbons, and then we see how many carbons are attached to the bridgehead carbons. So these are 2 purple carbons, 1 green carbon here, and 1 blue carbon here. So if I write in descending order, so first comes 2 purple, dot, 1 green, dot, 1 blue. And then I put square brackets around it, and in front of it I write Bicyclo, and I end the name with the suffix which includes all the carbons. So how many carbons do I have? 2 plus 1 is how much? 2, 3, 4 plus the 2 bridgehead carbons, 6. That's why the name hexane. What about this next structure? The same principle. 2 bridgehead carbons. There are 2 carbons attached on this side. There is 1 green carbon here, and there are 2 blue carbons on the top. So the name is 2 for blue, dot, 2 for purple, dot, 1 for green in the square brackets. And let me write the square brackets in black. Bicyclo in the beginning because it is a Bicyclo compound. And then total number of carbons, it's 2 plus 2 plus 1, 5, plus 2 bridgehead carbons, 7. So it's heptane. Next, again there are 2 bridgehead carbons here, 1 blue carbon here, 1 green carbon here, and 1 purple carbon at the top. So let me write. So all are 1. So 1 comma green comma, and 1 more is blue, and I write a square bracket. It's not comma actually, it's dot. Okay, anyway, so the total number of carbons are 1 plus 1 plus 1, 3 plus 2 bridge carbons. So it's 5, so it's pentane. Fine. What about this next structure? It's written in a different way. So here these are the bridgehead carbons, and there are 2 green carbons here, and there are two purple carbons here, and there is one blue carbon at the top coming out of the page. So again it's 2 comma 2 comma 1 heptane, and it's bicyclo. Why heptane? Because total number of carbons are 2 plus 2 plus 1 plus 2 bridgehead carbons, so it's total number of 7. What about the next compound? Identify the bridgehead carbons. Look at how many carbons are attached to it. One carbon, blue carbon here, one purple carbon here, and two green carbons here. So in decreasing order it's 2 comma 1 comma 1. So 2 plus 1 is how much? It's 4 plus 2 bridgehead carbons, so it's 6, so it's hexane and bicyclo in front. What about this? Let me do it quickly. 2 bridgehead carbons and 2 purple here, and 1 2 3 4 here. Okay, and there is one more bridge here, but which has no carbon. There is nothing pointing out of the page, so it has 0. Let me write down in different color. So let me use green. So unlike the problems or the structures that we just dealt with, where there was at least one carbon on every side of the bridgehead carbons, see, this side of bridgehead carbon had how many? It has 2, this has 4, but this doesn't have any, it has 0 that I have to mention. So in decreasing order it's 4 comma 2 comma 0. So total number of carbons are 4 plus 2 6, 6 plus 0 is 6, plus 2 bridgehead, so it becomes 8, so it's octane. Similarly here, these 2 red carbons are bridgehead carbons. This is the purple carbon, and these blue carbons are here, and on the other bridge, on the other side of the bridge, there are no carbon, that's why it's 0. There is no vertex there, so the total number of carbons are how many? 1 purple and 3 blue and 0 green. So in the decreasing order it's 3 comma 1 comma 0. 4 plus 2 bridgehead, it's 6. So the name is bicyclo 3 comma 1 comma 0 hexane. Let me come to the next slide where we have some substituents. So whenever you are considering bicyclo compounds, and if there are substituents, you need to give the locants. Now how to give the locants? Now whenever you have bicyclo compounds, you always start numbering from one of the bridgehead carbons, and then you proceed to the larger ring first. Important, proceed to the larger ring first, and then you come around and go to the smaller ring and finish your numbering. Now the next thing that is to be thought of is about the lowest sum rule. Now that is done according to the different situations we have. Let me explain. The first structure, I start numbering from one of the bridgeheads and then proceed to the larger ring, and then I come to the smaller ring and finish numbering. Now in this way I got 8 for the substituent. There is one more way, there is one more bridgehead at the bottom. I start there and then again I go from the larger ring and then I finish numbering on the smaller ring. Now in this case I got substituent at carbon 7. So the lowest sum rule says that we have to have lower sum of all the locants, and here there is only one locant because there is only one substituent, and in the first way I got 8 and in the second I got 7, so 7 is correct. So we get 7 methyl, and the rest of the naming is done already in the previous page, so I will not be covering. So the correct way of numbering is the purple and not green, because that gives me number 7 and not 8. So that's how numbering is done. Let me look at the next structure. I start numbering at one of the bridgeheads, say the bridgehead at the top. I give it number 1. I go around the bigger ring. I finish numbering, and then I come to the smaller ring. Now here I got substituent at carbon 2. Now if I start at the bridgehead carbon at the bottom and I go around the bigger ring first and then finish numbering, I got the methyl group or the substituent at carbon 5. So which is correct? According to lowest sum rule, the purple numbering is correct. So the name is, that's why, 2-methyl bicyclo 4.2.0 octane. What about the next structure? I start at one of the Bridgehead Carbons. Say I do it with blue. So I start here, 1. I come around the larger ring first. I finish the numbering on larger ring, and then I come to the smaller ring. So I got the substituent at carbon 6. So let me do an alternative numbering. So I start at the bottom and I finish, and I still get the substituent at carbon 6. So either way, the name is 6-methyl bicyclo 3.1.0 hexane. So let us go to the next structure. So I start at one of the bridgeheads, 1. I go to the larger ring, I finish the larger ring, and then I come back to the smaller ring. So here I got the substituent at carbon 2. If I do from bottom, I get the substituent at carbon 4, but I prefer 2 according to the lowest sum rule, so that's correct. So the answer is 2-methyl bicyclo 3.1.0 hexane. What about this next structure? Until now we had structures in which there are only 2 rings we were considering, the larger ring and the smaller ring. There was a third bridge even in the previous structures, but it had 0 carbons, so we didn't bother numbering on the third bridge. So there was only bigger ring and smaller ring. But here we have 3 bridges with at least 1 carbon, so I need to number. So I start at Bridgehead Carbon, so I give it number 1, and then I come along the largest bridge. But here we have 2 large bridges, right? The bridge on the left has 2 carbons, and bridge on the right also has 2 carbons. So I can start numbering from the bridgehead, and I can proceed to the left or to the right, it doesn't matter. So if I proceed to the left, this would be the way I number. So I come to the left first, and then I go to the right, because at the top you have the smaller, so I should go. Or I can start at the left and come to the right. So anyway, you'll get the right answer, but sometimes you have to decide between going to the left first or right first depending on the substituent. So here the substituent is at the top, so it would not matter. So I'll start at the left anyway. So I'll complete the numbering, and then I'll come to the second largest bridge, which is on the right. So I'll continue with numbering there. So after 4, 5 comes on the right and not on the top. So 5 is written here. Let me write it down. So this is 5, and then 6, and then the remaining number will go on the top. That is 7, where the methyl group is attached. That's why the name is 7-methyl bicyclo 2,2,1 heptane. What about the next structure? In the next structure, if I start at the Bridgehead Carbon, and if I come from the big ring on the left and then go to the right and then finish at the top by giving the topmost carbon as 7, I get the methyl substituent at position 6. And instead, if I start at the same Bridgehead Carbon as I started before, but if I start numbering from the right instead, because that too is the biggest bridge, I get 2 at the substituent. So which is better? Is getting 2 better or getting 6 better? Or which is right? Getting 2 is right, because according to the lowest sum rule, the substituent should have the lowest locant. So the blue numbering is correct and the purple is wrong. I can also start at the Bridgehead Carbon at the bottom where we have number 4, but that would anyway not give me the lowest number. So this blue numbering is correct, and thus the name. What about this next structure? If I start from one of the bridgeheads, I have 3 bridges which are of equal sizes, so I can proceed wherever I want to, because I should start with the largest and end with the smallest, but here all 3 are same. So I start from the top because there is a substituent at the top, and I wish to have the lowest possible number to the substituent. So if I number it starting from the bridge on the top, I get carbon number 2 there, and then 3 where the substituent is attached, and then I can finish numbering. But instead, if I start at the Bridgehead Carbon at the bottom, I'll get a lower number. Let's see, I give the bridgehead at the bottom as number 1, and then go to the top. Now here I got 2 instead of 3. Now what is the correct way of numbering. Was the last way correct or this way correct? Now I can finish numbering, but it doesn't matter because I got the locant for my substituent. So it's 2 and the answer is 2-methyl Bicyclo 2,2,2-octane. So that is how numbering is done. What about this next structure? Let me see the next structure. In the next structure there are 2 substituents. So there are 2 methyl groups. One is attached to the bridgehead carbon itself. So that should get number 1 because that will give me the lowest sum. And then I should proceed from the top because I can proceed anywhere because all the sizes are same. I have to go by decreasing order, but here it doesn't matter. So I start counting from the top. So it's carbon 2 on the top, then 3, then 4. Then I can finish numbering. It doesn't matter because there are no more substituents. So I have 2 methyl groups, one at carbon 1 and one at carbon 3. So the answer is 1,3 dimethyl 1,3 dimethyl Bicyclo 2,2,2-octane. So that is how the numbering is done here. So let me go to the next slide. So we have Spyro compounds here. So how are Spyro compounds different from Bicyclo compounds? In Bicyclo compounds, 2 rings are connected by a bridge. The bridge may have 0 carbons, 1 carbon or 2 carbons, but in Spyro compounds, 2 rings are connected by a common carbon atom. So why are these called Spyro compounds? Because they twist like spiral structures when they are viewed in spectroscope. Anyway, how to name these Spyro compounds? Let us see. In order to write the name of a Spyro compound, you have to first identify which the common carbon is, which is quite easy to see. The carbon that connects 2 rings is the common carbon atom. So while dealing with Bicyclo compounds, you first identified the Bridgehead carbons and then you saw how many carbons were on each bridge. Now in Spyro compounds, you first identify which the common carbon atom is. So in the first case, it's the carbon that attaches 2 rings. So it's this carbon, and then you leave it and you see how many carbons are attached to that carbon on the either side. Now you look at the left. If you look at the left side, there are 1, 2, 3, 4 carbons. And if you look at the right side, there are 1, 2, 3, 4, 5 carbons. Now you write these numbers in increasing order. Unlike in Bicyclo compounds where you write it in decreasing order, you write this in increasing order now. So it's 4.5. So you write 4.5 in increasing order. You write square brackets around 4 and 5. And then you count all the carbons. So the total number of carbons are 4 plus 5, 9, plus the common carbon, so it's 10. So you finish the name by writing the name of 10 carbon compound, which is what? Decane. And in front of the square bracket, you write Spyro to signify that this was a Spyro compound. Next, if I go to the next structure, there are 2 carbons on the right side and there are 3 carbons on the left side. So in increasing order, it's 2, 3 or 2.3 actually. And we write square brackets, and then the total number of carbons are 2 plus 3, 5 plus the carbon that is common, so it's totally 6. So you write hexane at the end, and in front of the bracket you write Spyro. So that is how naming is done. Now if we have substituents attached to Spyro compounds, we need to number the carbons. Now how to number the carbons? Last time we started numbering in Bicyclo compounds and we started numbering from largest ring first or the largest bridge first. But here in Spyro compounds it's the opposite. You start numbering from the smallest ring first and then going to the bigger ring. So the rule is opposite here in Spyro compounds. Now we don't start numbering on the common carbon, we leave it as it is Unlike in the Bicyclo compounds where we started numbering from the Bridgehead carbon, here we don't start numbering at the common carbon. Here we can start numbering at the Bridgehead carbon because when we come around, we pass through the second carbon and there is a path. But if you start numbering here, then after you finish the smaller ring, there will be discontinuation in the path. So you leave that, you leave the common carbon and you start numbering from the first carbon on the smaller ring, and then you come back, then you'll have the way for the fifth carbon here. So you number it 5 and then you continue with 6, 7, 8, 9, etc. on the larger ring. Now after coming here, I can proceed counting from the top or the bottom depending on the situation required. So last time also we have seen that depending on the place where substituent is attached, we can decide from which path to move or to which path to move. So here when I come at 5, should I go at the bottom or should I go at the top for counting or the continuing the count? So because the methyl group is attached at the top, I will go there and number it 6, 7, 8, 9, 10. This is how I number the compound. So the name is 6-methyl Spiro 4,5 decane, because there are total number of 10 carbons present in the main structure or the parent structure of the compound. Let me go to the next structure. So I leave the common carbon, I start numbering on the smaller ring. So I give it number 1. I can give it number 2 also, but I wish to go by the lowest sum rule, so I start numbering at the top. I don't start numbering at the bottom, so I get 1-methyl, whatever the rest of the name is. So next I leave the common carbon, I start with the smaller ring, and obviously I'll start on the side where methyl group is attached or the substituent is attached, so that I get the lowest sum. I satisfy the lowest sum rule, so the name is 1-methyl Spiro 4.5 decane. And in the next structure, I start here. I should go to the smaller ring first, so 1 and 2, then 3 comes to the common carbon. Should I go at the top or should I go at the bottom here, or should I go at the left or should I go at the bottom? I'll go at the left because that will give me the lower number to the substituent, that is 4. So answer is 4-methyl spirohexane. What about the next compound? So this is the common carbon, I must leave it. So there are 2 equal rings attached, so I can choose whether I take the left first or right first. So because the substituent is attached on the left, I prefer to go to the left first, and I start numbering from the top, not from the bottom, because that will give me the lower number. So this is 1, 2, 3, 4, 5, 6. I can finish numbering, but it doesn't matter. So because I already got the locant for the substituent, so it is 2-methyl Spiro 5.5 undecane. What about this compound? This compound is what? Okay, let me just check it. So this is fine. Anyway, the next structure also has 2 equal rings. The next structure also has 2 equal rings, so I can start anywhere. So I prefer to start it right because that is where the substituent is attached. So I get methyl on carbon 1, so it's 1-methyl Spiro 5.5 undecane. So this is how we do the nomenclature of Spyro compounds. So there are 2 rules that are opposite. The order of numbers inside the square brackets are in increasing order, unlike in bicyclic compounds, and the numbering while you give the locants is also opposite to the way you do in bicyclic compounds. Here you start numbering from the smaller ring first and then you go to the larger ring. So this is how the nomenclature is done.